Alright, this will be a quick video to demonstrate the use of the direct analysis method using robot structural analysis. Now I'm starting to use robot structural analysis pretty much for the first time this year. I'm familiar with the program just a little bit in terms of past usage, but now I'm starting to kind of dive into it a little bit more. What I like about robot structural analysis by Autodesk is the fact that you can link your model directly to Revit and essentially take advantage of that interoperability between the two softwares and go back and forth between Revit and robot structural analysis. So I think it's a direction that our industry will be heading in more and more, is being able to link the structural analysis model to the actual, I guess, project design model, so to speak. But as we go into that area, we'll need to pay detailed attention to the analytical properties of our Revit structure model just as well. Or we'll just be using it for a certain stage. Anyway, let's get into it. So I will start a new model. By the way, let me just go ahead and show what version of robot structural analysis I'm using here. This drop down menu should provide me this information. Alright, so it's not doing it, but let's go to the help, and here's the information section. You can see I have the latest version of it right here. Alright, so I'll start a new model by clicking on new project. When you do that, of course, Autodesk gives you an option of the different type of structures you can use as far as starting as a template. And here, this is for typical what we would use for building design. This is for something more generic as a 3D frame design, so forth and so on. So let's use a 3D frame design for our tutorial here. Quick overview of the interface. Of course, we have our drop down menus up at the top, followed by icons down below, and more of the same. These are sort of like selection drop down boxes. As we create the model, you'll see how these areas are used. On the left hand side, we have what are essentially like explorer menus, if you will, or boxes. So similar to Revit, we could explore different aspects of the models using these features right here. By default, I believe on the right hand side you might have also some floating toolbars that are loaded up. The key feature, I guess, as far as the drop-down toolbars are concerned, is this area right here, this box right here, that allows you to essentially go into different modes, if you will. Alright, so this is when you're starting a structure. This mode might be, this mode right here might be for when you want to look at results. You switch to that mode and you get certain options, or when you want to go into design, you'll switch into that mode. It's asking me which design mode that I want to go into, steel / aluminum in this case, and then you'll notice that the screen changes dynamically through that process. Alright, and you have some other dialog boxes and toolbars that appear. When you're creating your model, you want to be into the structure model mode in the start. Okay. there are some other videos that are out there that can tell you more regarding the user interface. I want to kind of make this a short video, relatively speaking. Just like Revit, you can take a look at your model in different dimensions using this cube, or I believe if you hit the shift key and your middle mouse button, you can rotate. You'll see as we get into it a little bit more. Alright, so if you hit this front view, you may it had before some grids and some rulers that were turned on. If you're faced with that the first time when you get into the model, see if we can reset it, then you can turn it off if you don't like it. Alright, here it just disappears. Also, Robot Structural Analysis does some weird things. I still feel like they have bugs that they need to clean up at Autodesk, but like I said, I think this software has a lot of potential here. Alright, so when you start your model, one of the first things you want to do, of course, is set your preferences. So here we'll set our job preferences by going to the tool and drop down and select job preferences. This is where you can set things like the units, the design code, and other parameters related to structural analysis and design. For me, I say, obviously you want to pay attention to your units that you're modeling in. This is the section where you can set the defaults. Not clear on what unit addition means as far as Revit is concerned. I mean, a robot, but you can go into their help and try to get it. But the important thing is that you have your dimensions unit set, force unit sets. That's the area you want to concentrate on. Database, these are the options that are available. You can load new database into your model by clicking on this button, but for what we're doing right now, it's already preloaded with AISC 15. We're good to go with that. There are a slew of other databases and loads, and like I said, other videos or help from Robot can provide you information on that. What we're doing, you want to pay attention to our design code. Self-explanatory. So in the US and most municipalities, we're using AISC 36010. Most places are still using 36010 because their design code for IBC is most likely still 2015, IBC 2015. Some areas are probably using 2018 just as well. Anyway, for what we're doing is 36010. For steel connections, they actually do not have the options for implementing any AIC right now. So these, I have to look into this a little bit more in detail, but I'm not too familiar with the implementation of the steel connections area. So I'm going to leave that alone for now. Get into that in the future. Timber, reinforced concrete, all self-explanatory. For loads, this is where you want to pay attention because you might get an error if you don't have these settings matching other settings, other preferences later on. So you want to, if you're going to use allowable strength design method, you want to make sure you have that selected here. It's already there for my defaults. These are defaults that I have saved and use for most of my projects. So, but your robot structural analysis default may be different. Either way, to change them, you come here, and to save those current parameters as your defaults, you would do that using that button. Structural analysis. This is modal analysis, nonlinear analyses, and the parameters of this analysis can be set here. Again, the defaults are different. This is what I use. I use a certain number of load increments just because of that's the way I do things. Anyway, so it starts with 5. I like to use a little bit more load increments, and these increments are basically, my understanding is the division of the loads into the number of steps, if you will. So if you had 100, you'll be loading the structure with 10 at a time, 10 kips or whatever is the case. Other things are related to the parameters that can be explained really using the help from Autodesk. All right, the tolerance and things of that nature, all this stuff is set here. You can see it has a low value for its tolerance here, which is very good. Seismic analysis, that's for another video. Working parameters, that's irrelevant for what we're doing. Meshing, you can leave the defaults as it is right now. It doesn't affect what we're doing right now. We'll get into some mesh aspects as we create the model. So that's it. Nothing special has changed here. So just a quick overview, the units are fine as it was out of the box for what I have. The database was fine. The loads, the most important thing, as I said, is this load combination, this code combination area right here. All right, make sure it matches what you're going to use for design. So we say okay. Just a quick look, other preferences. In terms of setting your screen, you can set these different preferences here. I'm not going to go into great detail, but just a quick change of scenery. You can see if I accept that changes the screen. I like to use this dark green setting right here. So that's what we're going with. Let's save our structure. I'll make this my simple cantilever column, model number 4. Okay, so with Robot, you can just come in here and put your coordinates for your nodes. This is very similar to what you can do in Riza and also in STAAD. All right, you don't necessarily have to use grids like in SAP 2000. So I'll put in 0, 0, 0, my first node. You have to use commas to separate it and don't make mistakes. Alright, this is X, Y, and Z, our standard convention of coordinate system definitions. So we'll say okay, add that node, and you get a tiny little green dot. I don't like the graphics with the nodes, but that's life. After a while you get used to it. So if I'm going to model a column that's 12 feet high, so I'm going to put 0 for the X, 0 for the Y, and the elevation in Robot is in the Z direction. Our coordinate system axis right here gives us a reference. So here we'll go 12 feet. Units are shown on the right hand side. So add that node. Close it up. Could do this, and it's like it zooms in, right? You kind of don't see the other node, but it's right there. Kind of hiding behind some of the other stuff. Really want to improve that as far as the graphics, but you can actually turn on the nodal numbers and you can see it a little better. You can increase the size of these numbers just as well by going to preferences. At least this is how I do it. There are different ways to kind of skin the cat over here. So you can set this as your default. You can increase the number size. Let's say I want to make it 8 in this case. Accept that, and the node number increases in size, the font of it. Alright, now draw your member just like you would do in any other software, as far as any other generic software. Draw it from node to node. Of course, this dialog box appears, and I have all of some of these default settings. Right now I just drew in a member that is a W24 by 76, and it has default material property is still this member type. This is something that I think is relatively unique to robot structural analysis, but it essentially provides you with the parameters that are used for design. Alright, so you actually have to define a member type. I'll show you what I mean. This is a predefined member type that comes out of the box with robot structural analysis. Simple member. We'll get into it, but you can define something different over here if you wanted to. Alright, but talk about that in a second. And this is not the member that I'm actually going to use, and I'll show you how to modify that. Okay, but before I do that, I'll just go ahead and put a fixed support at the base of our cantilever column. Out of the box, the way you can do that, you come over here and go to support. I believe you can also go to geometry and get to this support option from that drop down menu. If you want to create a new support, you use this little page icon, and it'll allow you to kind of customize whatever support that you need to use for your analysis. Okay. Out of the box, it comes with fix and pin. Fix and pin, I believe you could double click on this and take a look at it. And fix is what you know fix to be when you learned it in statics. Okay, pin, so forth and so on. So we can select this thing, and you'll see that our mouse has changed in terms of its graphic. It has a little icon here. So I'll go ahead and select our node, and it has this block that represents a fixed support. Okay, close this thing out. Look at it in 3D. In 3D, go home. Here we go. Go ahead and extrude the member to show it in 3D. You do that by clicking on section shapes down at the bottom. It's one way. If you want to see the member sizes, you can go to your view menu and go down to display. The shortcut keys are VV for this. You get here. You have a list of different options that are applicable. If you have some favorites, sort of like what they believe are your favorites, you can also customize this a little bit. Then you have model, nodes, members. Basically, you can click on different things, to get what you're looking for. It just takes practice. So here, I know that I can come here and show my section names by expanding that drop down menu. Apply. This is the way that Robot chooses to show it. I think it's okay. It's just something that takes a little getting used to. Now, when you select this element, it turns a different color, and you get these parameters over here showing up on the left hand side. You can make modifications to them here. So it's very similar to what you would see in Revit. Alright, you could double click on this, and here if you see, like, I want to switch the parameter, I want to switch the member to a different size. I don't have it listed here. I hit this question mark box, instead of being able to get it takes you to the help section, all right, which I don't need any help on it. What I actually want to do is, modify this to a different element. So how do we do this, right? You might think you could double click on it, and that might give you the options, but double click doesn't do that. All right, so how to do that? I will load in another section by going to Geometry, Properties, Sections, and we have this dialog box. So here I click on New Pages or New Section by hitting this little page section, and I get this New Section dialog box. The database has already been selected, as I said previously. One of the good things about it is that it allows you to pick based on sections, section type. So if you have channels or angles, you can kind of isolate that area. And now I want to load in this case, our 14 by 30, which matches what we have shown in other videos on my page. So I will add this in. I'm just doing this for consistency with other videos in the beginning. Alright, so we'll use the same section so that we get the same results. Now I clicked add, or did I? Yeah, I clicked add, and it added it to the kind of like the project database. So I say okay here. Close this. I can select this and add it directly here, or I can close it out. Right? Always save. Select the element again, and now I have it under my drop down list where I could just switch the section size. Right? Okay, so I have the section defined, but I don't have the material that I want to use necessarily here. Like I said, out of the box when I loaded it up, it came in with that section. You can modify it in different ways. Here, thankfully, you can actually just pick it from the drop-down menu. It's already there. We'll pick in a typical 899250 KSI material standard. Right, and if you're not using 899250 KSI and you're in the United States and you're a structural engineer, and you're using W sections, you're making a mistake, because that's what you're supposed to be doing. That's the most readily available type of material for W shapes in the US. So save that. And that's for new design. If you run across an existing building and you're running analysis, obviously you have to use whatever is there. But either way, the properties are the most important things. All right, so okay, so now we have the right column, we have the right material, we have supports. Let's go ahead and define some loads. You go to the load menu and you bring in load types. Okay, here's another, what I believe to be a quirk of robot analysis, is that what they call the load types, when you bring it in, it's actually saying load cases. These cases will actually end up being analysis cases. That's why we have this analysis type column on the right hand side. And for the nature of the load, it gives you, like these pre-selected options of dead, live, wind, snow, seismic, etc. Okay, it doesn't allow you, or at least I haven't figured out how to just have a generic load, just to say it's, other, for example, like you would find in SAP. So I don't mind using live for what I'm doing here. So I'll set my live load as vertical. Give it the same type for and label name. Add it. I'll do the same thing for a horizontal load. Add it. Okay. You can make modifications to it. You can delete it, things of that nature. No, I actually haven't used the modify button yet, so let me check that out. Modify. I think it's just going to allow you to change the name if you wanted to change the name. Like this, let's say I was doing, instead of horizontal, I wanted to call it lateral or something. I think it just changes the name or label when you hit modify. Alright, so nothing apparent here. Do it over here to lateral. Right there it is. It changed. Keep it. It's what I had. Really doesn't make a difference. Okay. So that's just providing the load case names. Now I have load cases that I can provide a load definition to. So I can, here, this is where you actually put in the load value. Now, whatever is selected here, these drop down, that's what load case that you're on. So pay attention to this drop down box right here. So I can click on these nodal values. All right, just a quick explanation of this load definition dialog box. These tabs are self-explanatory. You can put the concentrated loads at nodes, or you could put on the member or a surface if it were plates or walls. You can apply self-weight and things of that nature for that particular load case that you're using. So I want to go ahead and put in a vertical load under my vertical load case of 32.7. Why 32.7? And that's just because of the fact that I've calibrated this structure. I know the failing load of this one particular section at 32.7, just to demonstrate the code check values and taking a structure essentially to its ultimate load as far as allowable is concerned. Alright, so we'll add this value. Have to click on the node. You'll get, and it shows you that the node has been applied. So I'll go ahead and add a horizontal load same way. You have to go back and zero out anything that's already there you don't want to use. I want to bend this thing about its weak axis, so I have to put my load in my Y direction here, and I'm going to put 2% or 0.2% rather of our vertical load. In this case, that's 0.0654. You could do the math on that. Basically 32.7 times 0.002. You get that value. Hit add. Alright, I hit add here, and then you have to apply it. Close it out. Now there are various ways of making sure that the load has actually been applied to the model. You could take a look at it graphically. Alright, you can actually put in the load values, show the load values by clicking this little value button. There's different ways of getting to this thing just as well. And it displays the load for the load case, similar to what RISA would do. Okay, so this is nice. Robot structural analysis sort of kind of blended a lot of the things that I've seen in RISA and I've seen in SAP and not SAP, but really RISA and STAD, so to speak. Some of the other SAP features are in here, so it's kind of like the best of these softwares, and it's I think it has, like I said, great potential. Anyway, so another way of taking a look at this to make sure that your load has been applied mathematically, you could just kind of make sure that this information is here. You can go to the load table. It's a database. This will give you even more information, more detailed information as the loads that have been applied to the structure. So here, these are the load cases that has been applied, and this list is like as if it was like a member or a node. That's what that list stuff means. You can go into the help for Autodesk to find out more information. You can see our 32.7 has been applied in the -C direction, and our 0.0654 has been applied in the Y direction here with a horizontal load case. You can also delete it by essentially selecting the element and delete the row and hit and delete. Now notice I didn't even apply a self weight or anything like that to it. I didn't manually do this, but the structure did it automatically. The software did it automatically, and it applied it to the vertical case in this instance. Even though I defined my vertical load case as live, it still did it automatically. This is a quirk, again, I think, in the software, because it's not doing what the user wants it to do. Some of these things are automatic. You have to pay attention to it. I'm going to delete this for a second, okay? So I hit delete, and that goes away, and now I know I don't have my self weight included in my analysis right now for what I'm doing, or at least in that load case. I'm actually going to go ahead and apply the self weight manually now by creating a load case for my dead load, say call it self weight. Now I'm calling it, this is just a name. It doesn't, just because you say SW, that doesn't put self weight on your structure. Alright, this is just a definition, if you will. So at this load case, and the way you actually apply that is by going to load definitions. You select your element. You can select the element pre-selected. I think you can pre-select. All right, let me go ahead and select this thing, and it's asking me what to apply it to. Apply it to this member right here, and it's taken. Sort of just turns into this like little magenta view here. You give this magenta line. It's not really a good graphical indication, but it's not bad at all. To make sure that it's in there for sure, again, go to your load table, and you can see that self weight has been applied to the element. All right, hit this X to close out of that box. Okay, so now I have my loads. Let's go ahead and combine these loads, because we're going to be using our direct analysis method. And for what I'm doing right here, I'll just go ahead and call this load combination. I'm actually going to call it just graph. It doesn't really matter. V plus H. What you want to pay attention to is this combination type. It's a ULS stands for ultimate limit state, and SLS stands for service limit states. All right, we're using direct analysis. We're checking stability. We have to use ultimate limit states. Parameter wise, let's see. You click on that. Nothing needs to be changed. This is more related to seismic. So we'll say OK. We say OK here, and it pops up this other dialog box where you actually do the load combination. You can select them individually and bring them over, alright, or you can basically hit this arrow right here and bring it over. If you had unique factors that you wanted to apply, in our case, we're doing the direct analysis method. If the structure somehow I don't know, if you had some type of setup where you want to basically define the load combination for allowable strength as -1.6, you could do it here. But in our instances, using robot, that would be double counting, because robot take care of that internally. All right, so it takes care of that internally when you have the proper setting. So we could bring everything over with a factor of 1. All right, so hit apply and close it. Save your model. Now I have my load combination defined. You'll find it in the drop down box here. It's number 4. I can show it. Now you don't see graphically, you don't see the other horizontal load kind of showing up because it has been scaled. Alright. I never tried to zoom in, but I'll zoom into this a little bit and see if it shows like a tiny horizontal load. Yeah, you don't really see it. Okay, because it's so small compared to our 32.7 kips. Alright, now to see that load, alright, to correct that feature, if you will, you can go to our display, you go to loads, and then you hit uniform size of load symbols. Say OK and apply. Alright, now you can see that horizontal load on your structure. Okay, so almost to the finish line with this one. We have our load combinations defined and all that good stuff. Let's see here. I think at this point we can run the analysis. I'm sure we can. In fact, I'll go ahead and do it. But just hitting that calculation button is not really informative. Okay, so we want to come over here and take a look at our analysis types. All right, and you can see the load cases and combinations that has been defined. All right, these combinations that have been defined are listed here under the analysis tab. There are other tabs that tell you more about the model, the structural model, and these settings are related to basically how nodes are generated. We don't need to modify anything here. These are the tabs you can go through and learn about it through the help features, but it doesn't affect what we're doing. Here we can hit this direct analysis method button, and that will implement the direct analysis model. This is how Robot addresses direct analysis method. Alright, so when we actually, before we do that, let's come over here to our load combination section. This little arrow shows you what's selected. Now if I want to modify this, and I do because I'm running a direct analysis method model, I need to actually use a nonlinear combination of our horizontal and vertical loads. Alright, so you select that and then you hit change analysis type. You can just change analysis type dialog box, and you can choose different analysis types here. We're still using a static analysis, so I can say OK, and then we get this message from Robot Structural Analysis in this case, because we've already kind of ran something. So it says OK. It's nothing serious here, but it's just basically asking me, do I want to continue because I've ran an analysis? So yeah, so they got to do it over. So say yes. Come over here and we select our geometric nonlinearity, P delta. This is what affects our stiffness matrix for our structure. This geometric nonlinearity is the same as what we'll find when we use RESA. Okay, so this modifies the matrix, the stiffness matrix of the structure directly. Okay, so here we'll say, okay, now this is geometric, okay, not material. So pay attention to that. So we say okay here. The material aspect of it is taken care of when you hit this direct analysis method selection. Okay. So now we could say Let's check that box and check our parameters here. And again, here, this is where we need to make sure that our settings are the same. So previously I had allowable strength design set as my design code and load combination generation. I must also select that option here. These other aspects of it is when you kind of want the computer to automatically generate notional loads for you. I'm not using that here, so I will unselect it. When I unselect this, it's actually going to give me a warning during the analysis that I don't have any notional loads being automatically generated. That's fine. It doesn't affect my analysis. For our still members here, this is where we reduce our axial stiffness and our bending stiffness, our EA and EI here. So make sure that we have this apply factor radio button selected. We could do the same thing and put an additional factor here for tau sub B if necessary. But this is all we need for our demonstration here. So say OK. And go ahead and run the calc. Now we're good to go. Here's our message from Robot telling me that the generation of the notional load has been blocked. Do I want to continue? I sure do, because it doesn't affect what I'm doing. You actually get this error. This is when you select this error. That's what it's saying. It's not an analytical error. It's an error related to. That's my little one. So it's actually an error related to the fact that I haven't generate any notional loads. Okay, but other than that, there's no issue. Okay, and I'll show you by demonstrating what the results are. All right, but the analysis ran fine, and we could close this out. Close this out. You can also see here from going to the analysis and the calculation notes, take a look at a simplified view of what has happened in your analysis. Make sure you didn't get anything crazy happening, so you can review that here. You're a structural engineer with some experience. You'll be able to see whether or not convergence has happened, or if you have some type of instability in your model or something that caused your model not to function properly. The information can be displayed here. This is the short view of it, by the way. The long view of that same information is from Full Note. And again, you can find out more detailed information in this area if you were nerdy enough to want to know so. Alright, and a real structural engineer will definitely be interested in this information. Okay, you'll be a nerd. Say okay to this. Now let's go ahead and check our results. You can do that by coming over here and taking a look at our bending. One thing I noticed, hold on for a second, is let's see our direct analysis model here. Now let me see. You're supposed to get a little box here, so let me go ahead and run a design on this thing. I could go to design and say okay, well, go to still member design section, and that actually throws you into, like I said, that module. And you get this kind of weird looking graphic here. As I am going to, you see now, I'm going to just ignore this for a second as far as the graphics are concerned. Let's turn it off so maybe it could look a little better as far as this loads out. Actually use this way, turn it off. And figure out how to resize our support at another point in time, but these things just change on their own sometimes. Alright, so what I wanted to point out is now that I'm in the design module, I have a new little button that's here that allows me to show my direct analysis model view or not. Okay, you can see when I click that, graphically the support changed in terms of its scale. This is something that robot just does on its own. Anyway, so coming back here, taking a look at the important things, and if what's important is this parameter selection. It's applicable to the member that has been selected. I only have one member in my model here, so it's applicable to that one element. But basically, you can select that, and it will show you whatever member is there. It would show up on this drop down, whatever has been selected. So this parameter, what's important for structural engineers? Okay, this is where basically you define things like your buckling length that you want to use. So if I had a brace in between this thing and it somewhat, the computer wasn't picking up on it automatically, you actually can set the parameter here. You can create a new type by essentially changing the name. So I'll just call it, let's say, Leo's column, and let's hit save. Now I have a new member type, Leo's column, here that's been added. Okay, still under the simple member parameter. For whatever reason, there's like another area where you can change it. I'll show that in another video or as necessary, but it's not affecting what I'm doing. Okay. So again, let's just go back through this so you can see. This is where you change things like your CB factor if you wanted to. Click on this and you could change it based on a specific number you want to use, or the end moments at the member, or if it was a cantilever beam. This affects your lateral torsional buckling capacity for beams, so or that aspect of it. This is buckling. We'll talk about this type of buckling. What we're talking about is our flexural buckling for columns. Okay, so there are various limit states depending on the section that you're using. For a column, it can fail by yielding, it can fail by flexural buckling, torsional buckling, or torsional flexural buckling, or even limit states related to the slenderness of its cross section, which are local buckling states for the member themselves. So all these different states can control your structure. Okay, these aspects, these parameters are related to flexural buckling of columns. All right, y-axis, x-axis, you could do it by coefficient or you could do it by real value. Doesn't affect me. K value, we're using direct analysis, is 1.0, and that's the beauty of direct analysis method. No modifications of K is required because you don't have to figure out K. K applies to effective buckling method, if you will, effective length of method. All right, so we say okay to all of this. Save it. Yeah, modify. It doesn't matter. Nothing needs to be changed. Close this up. Say okay. Come over here. Whatever. That's fine. Nothing has changed. Oh, by the way, what's annoying is that you can't actually kill this box when you're in the design method. You can minimize it, but you can't close it out. Alright. So here, what you want to pay attention to, this is a calculation section. Robot breaks everything up into parts. Instead of having one dialog box to set everything, it has multiple dialog boxes. So here's calculation section. by calculations, excuse me, by calculations here, what we have, what they're talking about is our design calculations. So you still have to go back and set the configuration one more time for what you're doing for your design. So you have to set allowable strength design method under your calculation tab just as well here. There are other things like number of points. It's not going to affect what we're doing. Maximum slenderness ratios. These are our standards, industry standards, 200 LOR or KLOR, if you will. Not exceeding 200, not exceeding for compression, for tension, not exceeding 300. This is related to basically practical limits of handling slender elements in the field. Okay, so if you had something that was that slim, for tension cables, you actually will most likely exceed 300. But for compression, 200 is a kind of like a rule of thumb that the industry has developed over time. So we continue to use this as it has served us well. There are other aspects here that you can select for alternative verification methods. I'm not doing any of that right now. The units of the results, you could use what's default in the units in robot, or you could select code. For what we're doing, it's not going to make a difference, so I'll select code. Just because code sounds better than robots. So say OK here. On the calculations, when I hit that calculations, this is actually running the calcs on the element now. It gives me warning messages or just information here, and it's telling me that, attention, the second order analysis was carried out under 1.6 times the AISC load combinations, which is what we expect. For design by allowable strength design method, the results will be divided by 1.6 to obtain the required strength of the member, and that's what we also expect. This other message is relating to lateral buckling verification, and it's just telling me that the computer has not done that itself. That's fine. That's why I'm using that's why I'm using the direct analysis method for what I'm doing. I'm checking that out by the capacity. Okay. Again, the direct analysis method is a poor man second order inelastic analysis. So that's sort of how we're getting to it. Running a second order elastic analysis, okay? But modifying the parameters of that second order elastic analysis. Alright. Results. This is the meat and the potatoes, okay? So this is where it's telling me basically if my member passed or fell. And here you can see the ratio is 1.01. Take a look at some of my other models. You would see that 1.01 is the correct value for this column that has been modeled. You can double click on it, double click on that box, just that field itself, and it pulls up a dialog box of the results and give you information on how'd you get to 1.1, what controls. It calculates for combined bending, for shear, and it does some quick checks on KLOR. You can say OK to that. It says incorrect section because the section has failed. You can hit calc note, and you can get the simplified view of that same dialog box. Sometimes this thing acts up and it might actually kick me out. Yeah. Okay, so this is where Robot runs into a little problem with me, and somehow it tries to open up Revit structure when I do that. So I end up canceling out of this stuff. Actually might have to terminate the program altogether and open it up again. So you might experience this. So it's good that you're seeing what's going on the screen. You won't freak out. So I end up coming over here and actually terminating the program altogether, at the end of the task. It's really annoying. And my computer is actually a little bit slow. I'm using something that has an Intel i5, but it's strong enough to run all the different programs I use, so it's good enough. If it was an i7, you'll be great. So in task, go ahead and let's close this out, so I don't need this right now. Come back over here and bring up robot again. And robot might, sometimes when things fail, I believe Autodesk is aware of these issues. It will pull up like a file that's a temporary file that has been saved, and it kind of allows you to pick up where you left off. I save very frequently, and so I might not use that temp file because sometimes I think it might create other problems that I have. But anyway, so when that happens, this is automatically, this is what it tells you. Alright, so it's basically asking me, do I want to load up my temp file again? Nope, I don't. But you can. I don't, just out of my own practice. So I'll go ahead and open up the actual file, because the last time that I saved it was not probably too long ago. Alright, take a look at it right here. At 11:23 it was saved. So I'll just go ahead and pull it up. See where it left off. Okay, good. So it looks like we still have some good stuff in here. Let's go ahead and check our cases. They're all there. Alright, save the model. Now, go ahead and go to Design. Show both our cases here. Check our configuration. See, now that didn't take our allowable strength design, so we'll go ahead and save that here. Yeah, I forgot to explain earlier that basically these are the combinations that it's checking. I'm not doing anything related to deformation right now as far as limit states, so I don't care about that. Here's another little quirk. If you see, if you go to this strength area, you say you list. Sometimes this will say strength, sometimes this will say ULS. It's weird. Still haven't figured that out, but that's what it does. Anyway, so you could go to the list. This is supposed to be like a list of the load combinations that's selected. Alright, this is where the software is similar to STAT. You can say all. Right, to load in all load cases, simple ones as well as combinations, and if you had groups it would load those in as well. Now I can say close. Now you can see that I've done this, right? I say close. What happens? Nothing on the screen. Right, so now I have to come in and put it in manually. I have to send a message to Autodesk about this. But see, I could come in here and try to do it even more manually. I'm thinking, well, it didn't take. So I'll just put in this load combination. This DAM-V plus H, so it's a direct analysis method load combination that was created automatically based on the combined loads and nonlinear status. So I bring this in automatic, right? So I put this in. And I'm saying, okay, close. It still doesn't show. I have to actually type it in. and then hit calculations, and it runs that calc based on whatever is selected in this area. So here we have the analysis and same results. I'm going to save before it kicks me out again, just in case. Now I hit calc note, and instead of kicking me out, it works. So I'll go ahead and pull up full note, and this is sort of like their calc report on that particular member. You can take a look at. Same information that was presented when you double clicked here. Okay. Alright. Alright, so that's essentially it, but just to show that this thing is consistent with previous analyses, you still need to break this member up into a few more pieces. Okay, so you still just have one element with two nodes here. So when you're using the direct analysis method, you again, for frame members, you want to break them up into a little bit more sections. Thankfully, that's not hard to do here in Robot. And actually, you only need to break it up into two pieces to get something that's closer to reality. Alright, so say cancel to that. Let's go back into our design, our start view. Okay, let's take a look at some things like results, right? So I haven't showed you how to take a look at shear force diagrams, bending moment diagrams, or anything like that. I'll do that right now. Even though I'm not in the design mode, I can still take a look at that by going to results and diagrams for members. This NNT, I guess N stands for whatever it stands for. I think it stands for like axial, torsional, and moment. This is kind of weird, but that's what the designation is, so you could take a look at your traditional axial diagram, shear force, and bending moment diagram. So MY is what we want to take a look at. YMY, because you actually need to look at the bending about its weak axis. Turn on your local axis system. It is color coordinated with what's shown here, but it's not oriented the same way. So keep that in mind. X is red, Y is green, Z is blue. Okay, so I want to take a look at bending about, oh, I said MY, so in this case it's actually MZ. So take a look at that and hit apply, and I'll see my bending moment diagram about the y-axis. And I can show the values. It's really annoying, but you actually have to come over here and say show the labels. Now what am I looking at? How do I make sense of it? What I'm looking at is actually the values for the linear combination, the really linear elastic combination in this case. So it doesn't take, this isn't your actual design values. This 16.7 is not your design value, and I'll show you how we figure that out. So we hit our direct analysis method model, and now you see a different value here and a different bending moment diagram. Let me not show this in the extruded view so you can see it clear. So now we have a different value, and you can see that this value is 368.57 kip inches. Okay, units are set at different in different screens or whatever have you, but these are the kip inches value. Because we are using the allowable strength design method, this is actually 1.6, the 1.6 value. Okay, so we would have to divide this out by 1.6 to get what the computer is using for design. Okay, so you can see how do I know this basically, right? How does an engineer know that for a fact? So keep in mind this is like 370 kip inches. When I go to my design results, and I can take a shortcut and not have to switch by pulling up our calculations tab directly and making sure my settings are right and hitting calculations. This warning is what's related to this value right here. You come over here and you'll take a look at it. Let's just double click into this right quick, and you'll see that okay, it didn't show you the moment value here. What does it? See here it is. So for internal forces, it shows you a MRZ value, which is the required moment about the z-axis for this, of 230.36. Let's pull up a calculator. We'll take 368.57 and divide it by 1.6, and you'll see I have 230.36. Okay, I haven't figured out how to get Robot to show me that value directly, our design value directly on the screen as far as the bending moment diagram is concerned. So you always kind of have to do this little math in order to figure out what you're looking at. But if you watch my videos, subscribe to my channel, you will learn these things and you will not make huge mistakes at your job, okay, and cause anxiety for your project and possibly kill people. So we don't want to do that as structural engineers. This is why continuing education is extremely important, and my channel gives you the opportunity to learn more, I think. So we say okay to that, and let's go back. Same thing applies for deflection too, by the way. So you want to take a look at deflection. You will go to deformation. I like to put in all this stuff and say apply. We got our deflection. This is not the deflection. It's not 6.7. You actually have to take that and divide it out by 1.6, and you will get something that's closer to other values. Well, closer to the values that you'll find in other software, where it take care of that internally. So we'll say okay. Let's turn off our deflection for a second. Say that. Apply. Okay, so back to what I was doing in the first place was I want to show you the differences. Okay, so I'll turn off this, go to our start model. A lot of this stuff just stays on the screen on its own. I haven't figured out a button that could just clear everything all at once. So you still have to go back and kind of manually get rid of things. Alright, so I'll turn off my coordinate system, and I'll not show my deformation just as well. Alright, so to clear out things, I'll leave the loads shown. Okay, close this out. We're saying okay. Copy this over, and let's go ahead and create a few more of these cantilever columns. I'll create 3 more. I'll copy them over 5 feet apart in the Y direction, so it's 0, 0, 5, and 0. Hit execute. And we have that. Close it out. Now I will modify these elements. I'm going to take this and divide it into 2. I'll do that internally. The way you do that is by going to Edit, then you go to Edit again. I'm sorry, I apologize. You don't go to Edit again. That's when you're doing your copy. It's a double edit thing. You go to Divide. So come over here and select into parts, or just to divide into number of sections, and 2, and make sure you have this selected basically, and that's the way it'll take care of internal divisions and not split your memory into pieces where you're going to have to do more post-processing to the elements. We don't want to do that. This is what we want to do. Divide it into 2, hit execute, and I get a new node. I'll go ahead and select another. I'll undo that. Now I want to apply it to this. So let me close something. I'll hit escape and make sure nothing is selected. Just to do it manually. Come back and do it again. I'll divide this one into 4. Hit execute. And I'll divide and close this. Select it again. It's the only one selected. How do I know that? Also over here on the drop down box, it shows me what's selected. Come over here, I'll divide this one into 8 and hit execute. Now let's see how many nodes I need to converge on the same answer. Okay, everything else is the same. I go ahead and say calculate, either which way I want to do it. I kind of like to go through the manual process sometimes. Take a look at everything, make sure nothing has changed inadvertently. Alright, we're all good. I hit calculation. It's also going to tell me that the structure is kind of disjointed or separated. It's going to give me a warning about that. That's this warning. Separate structures. Do I want to continue? Yes, I do. Doesn't affect what I'm doing. It's telling me about the notional load issue. That's fine with me. I can show you guys also how to get rid of that. In fact, I'll do that after we run this analysis. Trick the program. Say yes to that. Separate structures again. That's fine. Might actually pop it up for each one of these things. Okay. So some people don't like errors, and we see this, and they get nervous. And I don't like errors either. So I'll accept warnings, but I don't like errors because it gives the wrong impression sometimes. You know, if you're in a court of law, somebody might say, "Hey, here it is. You had an error, and you're the one at fault now, structural engineer." Even if that error doesn't mean anything, the lay person is not going to know that. All they know is the definition of the word error. So let's get rid of this error. Okay, or that message. The way I like to get rid of it is by tricking the program by, in my mind, let's just say manipulating the program by coming over here and taking a look at my load case. Cancel out of that. Let's just stop. Sorry, I hit the wrong button. Coming over here, go to analysis and go to set parameters. Go back to direct analysis. I'll go ahead and allow it to generate it for the gravity load combinations. Matter of fact, I picked nothing. I think this is how I tricked it. So I get rid of the generation of the load, but I select this button so that at the very least it doesn't give me an error. We'll see if this works. It's not going to generate anything as far as any additional lateral loads, so it won't mess up something that is already set. And that's in this case, that's for my nonlinear load combinations. I don't want it to screw it up. So I say okay. Everything else is the same. Run the calc. Separate structures. Warning. blocked. That's fine. Now it's giving me a new warning that's telling me that for the selected direct analysis method options, no notional loads have been created. Do I want to continue? Yes. Separate structures. That's fine. By the way, you can scroll through it and you can see I don't have any errors now, but I have a number of warnings. These warnings don't affect my analysis. So now I can stand in the court of law and say I didn't have any errors in my analysis. So we say, okay, this is how I trick the software. Again, tips of the tricks of the trade, so to speak. So you learn that by visiting my channel. Alright, so we say okay to all that. Now let's take a look at the results. Let's go ahead and run the design on these elements. Oh, by the way, just real quick, you could take a look at your results. Like if I were to map this, right, look at the ratios. If I just hit apply, I'm only going to get information for one. That's the one that has actually been executed so far. So my new copies, I didn't do anything to them, so there is no content in it for the design ratio option. So filling in that content, I would come over here again. Now you see it's on member verification, just one. So that whatever is listed here is what it would do. Alright, so I want to verify all, so I have to select all here. Configuration, always go back and check that, make sure you're set. The list, I'm good with number 11. So say okay. I'll say calculate. Now I get calculations for it, and it gives me results for all three. You can see all the other members have kind of converged to 13% over stress. Just gonna pull up our SAP 2000 in the background real quick. Let's see. Alright, so I'll let that happen in the background. Again, I could double click onto this. You know, now it's 13% over stress instead of being 1% over stress, or yeah, 1% over stress in this case, 13%. So double click on this thing, take a look, and you can see I have larger moments than the previous one. I like to look at that graphically, so I can do that by going over here to diagrams again, checking out my MC value. Alright, hit apply, and I don't see anything. Let's see, come over here to parameters, could be NY. Let's just go back over here. Normalize, yeah, that's what it is. Hit apply. Oh, no, what it is that it's so small you can't hardly see it. I'm looking at my direct analysis. I'm looking at the other combination, so I have to click DAM model view. And now I have something that shows variations between the bending moment at the base. Okay, so you can see that the bending moment has increased, and it also has increased in terms of more accuracy, if you will, based on the number of elements that I had. So now I have a value of, with the one that is 4 and 8, SAP pulling up, of essentially 430 kip inches. Okay, and again, like I said, this is the modified value. This was actually 1.6, so you have to take this number and divide it out by 1.6 to get what the computer is using for design. But I'm not going to waste more time. Everything is right, and I'll show you just in terms of the maps. Come back over here. I'll map the ratio on the screen so you can see what we have here. And you see that it doesn't show anything. That's because I'm in the direct analysis view. Sometimes you have to click this like 2 times, 3 times, and it actually gives you what you need to see. These are the values that are used for design. How do you get to that? Make sure everything is right. There's go back to results and map on members. These are all little tricks that you have to struggle through sometimes when you don't know what to do. But you go to parameters, make sure everything is on, hit scale, automatic scale. Now this is based on different values that are shown, so I use simple. I'm going to say anything that's above 1.0, actually they'll all turn red at this case. Let's say, but this is how you do it basically. The reason why this is gray is because anything that was above 0.7 is set as gray. So let's set it at anything above 1.0, hit apply. Oh, if it's outside that scale value, is still gray. So let me demonstrate so you don't think I don't know what I'm doing. I want to modify this. I have it as 1.5 now. They're going to turn green. Alright. For some reason this didn't take. Weird, right? But I could come back over here and just set it as outside that value and say okay, and apply. And I guess it thinks it's outside that value. But you can see that it turned. Oh, no, I apologize. This is for whatever is less than. So it's these should still be green. For some reason it's not. But that's just the way the software is sometimes, and you have to kind of go in and out a couple times, and as you do different things it'll change to the color you want. Right? User settings, this is probably what's the problem here. So let's go with 1.5 and hit apply. There you go. Now they're all green. But green doesn't mean go here because I only want to see anything that's above 1.0. Say okay. Apply it. They're all over stress. I think you get the picture. Alright. Now let's check and see what SAP has for these very same elements. Pull up my SAP model on this. If I could do that real quick. I believe this is the one. SAP sometimes actually it's going to give me a different value because SAP has a little issue with checking at the right location, checking the capacity at the right location. But everything is the same. You could take a look at some other videos if you don't believe me. But we're looking at several different 14 by 30s columns, 12 feet long, bending about the weak axis. All the loads are the same. Right click on this and you'll see that I have the right load values in here as what's in my robot model. And I'll go ahead and run the analysis on this. Go ahead and show our stress ratios. And you can see our 13% here. These other two elements are different column sizes. I can get robot to do the same thing here just as well using those column sizes. Alright, so that's it. Bring this thing home. That's essentially how you use the direct analysis method in robot structures. This is the long version of the video, kind of explaining explaining some different features just so that you could, if you're new to the software, you can get the hang of it. I'll put up another video that's a little shorter in the future, but I think this one is good for a good learning tool if you're kind of new to the software. All right, so we'll save it. Let's just go ahead and do what works. Can't help it. I can't resist. Let's do what works. I'm not gonna leave out with something that doesn't work. All right, so I have this thing selected. I'll go ahead and copy. No, let's not do that. Let's just modify this element. That'll be the easy way. That way, it takes less time. Close it. Go to our start menu. Let's get rid of all this stuff on the screen. Let's see here. Boom, boom, boom. Turn off our, what I have shown, the diagrams. Turn this off. Apply. I have the stress ratios being shown too, but I'll leave it. Select this element. Change this to something that works by putting in another section. We'll use something that I would say is more traditional. Well, I'll just use the 16 by 40 since it's here, and I think it's in SAP as well. So I'll apply it to this member. Now it's 16 by 40, much greater capacity. Let's go ahead and run the analysis. Now we could just click on this because we know everything is set. Separate structure, warning, more warnings. Excuse me. So, okay, close. See that it's still showing old stress ratios here. Let's update that. See, this now works. Screen still haven't picked up on it. Quirks. Come back over here. I think you have to say apply, and now you'll see that we have our stress ratios that matches our calculations. Set 0.2. Come over here, take a look at 0.28 rather. Double click, save info, so forth and so on. Section is okay. And that is the end of this video. Peace.